This is the largest steam locomotive ever built, 1,200,000 pounds, 132 feet long, 7,000 horsepower. The driving wheels alone are over 5.5 feet tall. The locomotive is longer than 2 modern semi-trucks parked end to end. But the big boy is not famous because of its size. It is famous because of what is inside it. An engineering solution to a problem that was strangling the American war effort. The Wasatch Mountains of Utah, the steepest sustained grade on the Union Pacific Main Line. In 1941, that mountain was the bottleneck choking the flow of war material across the western United States. The big boy was the answer. And what is under the hood is the most ambitious steam engineering ever applied to a locomotive that actually worked. This is what is mechanically inside the largest steam locomotive in history, and why it is the only machine that could solve the problem it was built for. In 1941, the Union Pacific faced a specific operational crisis. The Wasatch grade between Ogden and Green River required helper locomotives on nearly every heavy freight train. 2, 3, sometimes 4 additional locomotives coupled in to push trains over the mountain. Each helper required its own crew. Each helper required servicing. Each helper had to be cut in at the bottom of the grade and cut out at the top. The operation was slow, expensive, and labor-intensive. And with the war effort demanding maximum freight throughput, slow was not acceptable. The Union Pacific went to the American Locomotive Company with a specific requirement: build a single locomotive that could haul a full wartime freight consist over the Wasatch grade without helpers. The locomotive that resulted was the big boy. What ALCO built to meet that requirement was a masterpiece of articulated steam engineering. Every component was sized to a single purpose, moving enormous tonnage over a brutal mountain grade, continuously, reliably, without assistance. The big boy's wheel arrangement was 4-8-8-4. 4 pilot wheels at the front to guide the locomotive into curves. 2 sets of 8 driving wheels each, 16 powered wheels total. 4 trailing wheels under the firebox at the rear. The critical engineering was the articulation. The locomotive had 2 complete engine units, 2 sets of cylinders, 2 sets of 8 driving wheels. The rear engine was rigidly attached to the boiler frame. The front engine was hinged, articulated, so it could swing left and right relative to the boiler as the locomotive negotiated curves. This articulation solved a fundamental problem. A locomotive with 16 driving wheels on a single rigid frame would be physically unable to negotiate curves. The wheelbase would be too long. The locomotive would either derail or be restricted to nearly straight track. By hinging the front engine, the big boy could put enormous power on the rails while still bending through curves. The boiler extended forward over the front engine, supported by a sliding bearing that allowed the front engine to swing while still carrying the boiler's weight. The front engine essentially steered itself through curves while the rear engine and boiler followed. The engineering challenge was maintaining steam and exhaust connections to the moving front engine through flexible joints that could survive the constant articulation. Steam from the boiler had to reach both engines. The rear engine was straightforward, fixed connection. The front engine required flexible steam pipes and exhaust passages that could accommodate the articulation movement without leaking under the boiler's 255 pounds per square inch of pressure. These flexible joints were among the most demanding components in the entire locomotive. The articulated design was not new. Mallet had patented compound articulation in the 1880s. American railroads had been building articulated locomotives for decades. But the big boy applied the principle at a scale that had never been achieved before in a successful production locomotive. 16 driving wheels, 2 engines, 1 boiler, all working in coordination to move tonnage over a mountain. The driving wheels were 68 inches in diameter, relatively small for such a large locomotive. The Union Pacific chose the smaller wheel size deliberately. Smaller wheels produced more starting tractive effort at the cost of top speed. The big boy was built to haul heavy tonnage over grades, not to run fast. The 68-inch wheels optimized the locomotive for its actual mission. Despite the optimization for power, the big boy could still run at over 60 miles per hour on level track. But the articulated frame was only half the engineering. Feeding 2 engines required a boiler unlike anything that came before it. The Big Boy's boiler was one of the largest ever fitted to a locomotive. It had to generate enough steam to feed two complete engines simultaneously at full power. A boiler that could not keep up would starve the engines. Exactly the failure that doomed the Erie triplex decades earlier. The firebox was enormous. The grate area, the surface where coal burned, was approximately 150 square feet. For comparison, a typical large steam locomotive of the era had a grate area of 70 to 90 square feet. The Big Boy's firebox was nearly double the size because it had to produce nearly double the steam. No human could hand-fire a firebox this large. The Big Boy used a mechanical stoker, a steam-driven auger system that fed coal from the tender directly into the firebox at rates that would have been physically impossible for a fireman with a shovel. At full power, the Big Boy consumed approximately 22 tons of coal and 12,000 gallons of water per hour. The firebox fed into a combustion chamber, an extension that gave the burning gases more time and space to release their energy before passing into the boiler tubes. The combustion chamber improved efficiency and helped the enormous firebox burn coal completely rather than sending unburned fuel up the stack. The boiler tubes carried the hot combustion gases through the water-filled boiler, transferring heat to generate steam. The Big Boy's boiler contained both small fire tubes and large superheater flues. The superheater took saturated steam from the boiler and reheated it to higher temperatures, increasing the energy available to the engines and improving overall thermal efficiency. Steam generated in the boiler passed through the superheater, then to the throttle, then to both engines. The rear engine received steam through fixed piping. The front engine received steam through the flexible, articulated joints. Each engine had 2 cylinders, 4 cylinders total, each 23 3/4 inches in diameter, with a 32-inch stroke. At full power, all 4 cylinders operated in coordination, each receiving high-pressure, superheated steam, each contributing to the locomotive's total tractive effort of over 135,000 pounds. The exhaust beat of a Big Boy at full power was the sound of 4 cylinders firing in sequence, a rhythm that defined the locomotive's mechanical character. The tender that carried the coal and water was itself one of the largest ever built. It rode on 14 wheels and carried 28 tons of coal and 25,000 gallons of water. Even with that capacity, a Big Boy working hard over the Wasatch grade needed servicing frequently. The locomotive's appetite for fuel and water was as extreme as its power output. All of this engineering existed for one purpose: to move tonnage over a mountain that no other single locomotive could conquer. The Big Boy produced a starting tractive effort of approximately 135,000 pounds. This was among the highest of any steam locomotive ever built. The figure mattered because tractive effort, the force the locomotive could apply to start and move a heavy train, was the exact capability the Wasatch grade demanded. A Big Boy could haul a full wartime freight consist over 3,000 tons over the Wasatch grade without helper locomotives. The operation that had previously required multiple locomotives and multiple crews could now be done by a single locomotive and a single crew. The labor and time savings were exactly what the war effort demanded. 25 Big Boys were built between 1941 and 1944. All 25 entered service on the Union Pacific. They worked the Wasatch grade and the Wyoming Main Line throughout World War II and into the post-war era, moving the freight that supplied the American war machine and the post-war economy. The Big Boys were not confined to the Wasatch. They worked across the Union Pacific's mountain territory in Wyoming and Utah. They hauled freight at speeds up to 60 miles per hour on level track and ground-up grades at a steady crawl under full load. The locomotive's versatility, extreme power combined with reasonable speed, made it valuable across a wide range of operations. The Big Boys were demanding to maintain. The articulated joints required regular inspection. The enormous firebox and boiler required careful attention. The locomotives consumed fuel and water at rates that required substantial servicing infrastructure. But the Union Pacific accepted these demands because the Big Boy delivered exactly the capability it was built for. The Big Boys operated until the late 1950s and early 1960s. As diesel locomotives took over the Union Pacific's freight operations, the Big Boys were gradually retired. The last revenue run was in 1959, though some were retained in reserve through 1962. Of the 25 big boys built, 8 survived into preservation. 17 were scrapped. The 8 survivors became static museum displays scattered across the United States. Beautiful, enormous, and silent. For over 50 years, no big boy operated under its own power. In 2013, the Union Pacific announced something that most rail historians considered impossible. They would retrieve big boy number 4014 from a museum in Pomona, California, where it had sat outdoors for 54 years, and restore it to operating condition. The restoration took nearly 6 years. The Union Pacific's steam shop in Cheyenne, Wyoming, disassembled the locomotive almost completely. The boiler was inspected and repaired. The articulated joints were rebuilt. The running gear was reconditioned. The locomotive was converted from coal to oil firing to simplify operation and servicing. In May 2019, Big Boy 4014 moved under its own power for the first time since 1959. The largest steam locomotive ever built, a machine that had been a static display for over half a century, was operational again. Today, Big Boy 4014 operates on Union Pacific Mainline excursion service. It tours the United States, drawing enormous crowds wherever it goes. It is the only operating big boy in the world and the largest operating steam locomotive anywhere on Earth. The engineering that made the big boy work in 1941 is the same engineering that makes it work today. The articulated frame, the enormous boiler, the 4-cylinder drivetrain, every component that ALCO designed to conquer the Wasatch grade is still doing its job 8 decades later. The big boy represents something rare in extreme engineering. Most locomotives that push the limits of their technology failed. Too complex, too unreliable, too expensive to operate. The big boy pushed steam locomotive engineering to its absolute maximum scale and succeeded completely. It did the job it was built for the entire steam era, without compromise. What is under the big boy's hood is not just the largest steam engineering ever attempted. It is the largest steam engineering that actually worked. The articulated frame and the enormous boiler were not experiments. They were solutions. And they solved the problem so completely that the largest steam locomotive ever built is also one of the few that still runs today. The Union Pacific Big Boy is the largest steam locomotive ever built and one of the greatest achievements in articulated steam engineering. It pushed the technology to its absolute limit, and it worked. That combination of extreme ambition and complete success is what makes it the perfect place to begin this series. This is part 1 of our What's Under the Hood series, examining the mechanical engineering inside the most significant locomotives in American railroad history. Part 2 covers the Pennsylvania Railroad GG1, an electric locomotive whose drivetrain was so durable it operated continuously for over 50 years and survived an accident that should have destroyed it. Different technology, same engineering excellence. Subscribe so you do not miss it. There is more about American railroad engineering than any single video can deliver. Each of these locomotives deserves a full mechanical study. We are working through them one at a time.